Hi everyone. Okay, so this is a lesson about tangent lines. So we're kind of adding on some rules to what we've already talked about. We've talked about three main things, and I just want to list them out for you. So we started talking about central angles last week, and we also talked about inscribed angles. Remember, central angles is when you come from the center and have an angle that goes like this. An inscribed angle is when it has a vertex on the circle. If this angle is 20 degrees, then the central angle is 20 degrees. If this arc is 20 degrees, then the inscribed angle would be 10 degrees. Okay. We also talked about arc length and how that is a portion of your circumference. All right, so you'd be using the formula 2 pi r, which is circumference, and then you would be taking some portion of it. Okay? All right, so I wanted to start by actually going over one of your homework questions in case you needed some help with 11, 12, and 13. So if you don't need help, you check the answers and you're good. You can just fast forward through this. All right. You should be setting these two expressions equal to each other. Since they open up to the same arc of BA, they must be equal angles. So this arc is the intercepted arc for this angle and for this angle, which means they must be the same. When you solve, you should get that x is 6. Substituting back in, if x is 6, this angle is 13 degrees, which means this angle is 13 degrees, which means then your arc must be double that, so 26 degrees. Okay. Find the measure of arc BA. Well, we just figured that out. It's 26 degrees. So we move on to the last one. In this one, we want to know what the length of BA is. So you should always start by writing out your formula. So arc length equals 2 pi r times theta out of 360. Okay, again, we talked about this yesterday. We need two things. We need r and we need theta. Well, theta I already know is 26 degrees, but I need to figure out my radius. Now, my diagram, I can't figure out my radius, but I can figure it out since I know that the area is 140. Okay, so again, start with your formula. To find the area of a circle, it's A equals pi r squared. So that means my area is 140, which equals pi r squared. All right, I have to divide by pi first. So I get 140 divided by pi equals r squared. Take the square root. Technically, I get two answers, plus or minus, but it's not possible to have a negative radius. So my radius equals, and I'm going to leave this as an exact answer, 140 divided by pi and the square root of that. Okay, so if I go back to my arc length formula, I'm going to say my arc length is 2 pi times my radius times 26 out of 360. Okay, now here's how you can get an idea or check and see if what you're doing is right. The circumference is 2 pi r, so the circumference is 2 pi times my radius. It should be this. So if that's my circumference, then I obviously need to be smaller than that, which is why I'm multiplying this by 26 out of 360. And you can see 3 is definitely less than 41. So this would mean that BA is about 3.03. And then since this is a length, I need to include inches with it and not an angle, not a degree measure. All right. All right, so let's move on to the new material. So we're going to talk about tangents and chords today. Those are the two things that we're adding on, and they give you a couple properties. All right. A chord is defined as a line segment connecting any 2 points on a circle. So if I pick a point here and I pick a point here and connect them, that line segment is called a chord. I could go anywhere. I could go here to here, and that would be a chord. If this is the center of my circle and I happen to go from one side through the center to the other side, that's my diameter, and that is my longest chord. We like to be as specific as possible, so we call it our diameter, but technically it is a chord. Alright, it just has to stay within the circle, and it's got to be on the circle. It can't be like this in a point floating inside your circle, or it can't be something that goes like this. Okay? Some of our rules that we have if we have two chords that intersect each other. So notice that AB is a chord and CD is a chord, and they are intersecting at E. Okay, notice that from this point, from the line segment AB, you get two segments. You get this segment, which is AE, and you get this segment, which is EB. If I multiply those two together, so AE times EB, meaning their lengths, it's equal to, notice my other chord CD is broken up into two sections as well, X and 8. I can take X and 8 and multiply them by each other. So segment CE times ED. Again, notice their intersection point was E, so if I take this segment times this segment, it's equal to the product of the other two segments from the other chord. Okay, so I'll show you what that means. It means if I wanted to, I could solve for X. So AE is 6, so I would say 6, EB is 4, so 6 times 4 equals X times 8, or 8X. So 24 equals 8X, X equals 3. So that allows me to solve for X. Okay. Next, if I want, I can use chords to find angles. So what this means is, notice where these chords are. There's, at this point, there's this angle right here, DEB, and that opens up to arc BD. Notice that the vertical angle opens up to arc AC. So what happens is we can figure out this angle by taking half of those arcs, so half of arc AC plus arc BD, and that will equal angle AEC, which then is the same as DEB. Okay, so what that means in terms of numbers is I would take half of 30, because that's arc AC, plus 70, since that's BD. That gives me 100, and half of that is 50 degrees. So that means that angle AEC is 50, and DEB is 50. So both of those are 50 degrees. Alright, and that will hold true no matter where the chords are, whether they're the diameter or the longest or the shortest chords. Okay? Alright, so the important thing about that is that is inside the circle. Those angles, at least. Angle AEC is inside the circle. If we have angles that go outside of the circle, like this, we can figure out what this angle is, even though it's outside of my circle. Okay, sorry, this is not a chord. So what we say here is very similar. Notice that this angle, AEB, so this should be angle AEB. Notice that that angle, when it stretches out, the furthest that it reaches is this arc, and then it also intercepts this arc. So notice that there's two arcs inside. This one is obviously larger, and this one is obviously smaller. That will always be true. Whatever's closest to the angle is the smallest. Okay, so what we do is we say, very similar to what we set up above, half of arc AB minus arc DC will give us angle AEB. So the difference is adding versus subtracting. We add when the angle's inside, we subtract when our angle's outside. Okay, so let's say I said this was 120 degrees, and I said this was 40 degrees, and I would say half of 120 minus 40, and that means that that angle, 120 minus 40 is 80, half of that is 40. So this angle then would be 40 degrees. And no, those are not always congruent. That just was a coincidence. Alright, next we have secant lines. A secant line is a line that intersects a circle at exactly 2 points. So it must intersect at exactly 2 points. It's an infinite line extension of a chord. So meaning like this is a chord, excuse me, and then if I extend it and make it a line, now it's a secant. So a chord is a segment in a circle, and a secant line, we call it a line for a reason, is a line that intersects your circle at exactly 2 places. We say exactly 2 places because we can have a line that intersects at exactly 1 place. That is what we call a tangent line. So a line in the same plane as a circle that intersects a circle at exactly 1 point. This is called the point of tangency. It will never, never, never enter the circle. Okay, so what happens is in a secant line, when it hits twice, we call that line a secant line. When we see something like a circle and a line, it's implied that this is hitting at exactly 1 place, and then we call that a tangent line. This is the point of tangency. And what that does is it gives me this property. If from the center I draw a radius, or I could extend it, make it a diameter, it's got to come from the center. These two, the segment and the line then, become perpendicular to one another. So a tangent line is perpendicular to a circle, and it's got to be at its center. So you can't draw something like this and say it's perpendicular. All right, so perpendicular gives us a lot more properties. Right, because again, we can see that if I were to draw a triangle here, now I'd have a right triangle, and then all those properties with right triangles comes back like we did yesterday. All right, so let's flip over and let's go through some examples. First, let's identify and let's label every part on this circle. So we just talked about, this is the point of tangency, we just talked about this. This line outside that hits at exactly 1 place is called a tangent line. This line segment right here that comes from the center and hits the circle is called a radius. This line that hits here and hits here but extends outside of my circle is called a secant line. This segment that hits my circle in exactly 2 places, segment though, is called a chord. Okay. And this segment that goes from one side of my circle through my center to my other side is also a chord, but we always like to be as specific as possible, so we call this a diameter. And that kind of adds in all the things that we just talked about. All right, so let's do some algebraic examples. In number 1, I want to find x and y. I'm going to start with x. Okay, notice that I have 2 chords that are intersecting, and they're intersecting at this point. That means that this line segment times this line segment, so that's 10 times x, or 10x, equals this length times this length, so 11 times 5. So that means 10x equals 55, divided by 10, x equals 5.5. Alright, so now let's solve for y. Notice that y is an angle, and it's from the intersection of those chords. Notice that that angle opens up on both sides, because they're vertical, remember. Opens up to this arc, and this arc. Since this angle is inside my circle, I will be adding them. So I want to take half of 175 plus 35, and that will equal y. Okay, so 0.5 times 175 plus 35. So we get 105. So y equals 105. And we're going to do a lot of practicing with this property. Okay, and my next one, I again have 2 chords that are intersecting. They intersect at this point. So I have this line segment times this line segment, so y times 20 which is 20y, equals... All right, now we got to be careful on the other side. From that point, I have a length of 5. So 5 times. On this one, it's very easy to say a 2 or 16, but it's not from the center, it's from this line, so I have to go all the way across to my other side. So that's 2 and 16, which makes 18. So this means that 20y equals 90. So y is, I believe, 4.5. So y is 4.5. Okay. All right, if I want to figure out x, notice that at this point I have vertical angles. One extends this way, one extends this way. This is where different colored pens or highlighters or something might help. It intercepts this arc and it intercepts this arc. So you need both of them, one on each side. So I set up my formula. Since my angle is inside of my circle, I will take those arcs and I will add them. So 1/2 of x plus 125 equals my angle, which I have to figure out because I already have an unknown. But notice that if this angle is 47, then this one has to be 47. If I take 180 minus 47, I get 133. So that means that they're both 133. So then it's got to equal 133. Instead of distributing a 1/2, I'm going to double each side. That way I don't have to deal with a fraction. If I double 133, I get 266. If I subtract 125, I get 141. And there's x and y. All right, so both of those properties used the chord theorem as well as the angle inside when chords intersect. Okay. All right, and number 3, see what we have. We want to find the measure of ACD. That would be this arc right here. Okay. This point is not at the center, so I cannot say that these are central angles, but I can say that vertical, this is 80, and linear pair, this is 100, and this is 100. Again, not a central angle because notice 100 and 120 are not the same. If I want to figure out the measure of ACD, let's see. This is a diameter right here. So that means that this is a semicircle. So if I have 120 already, this has to be 60. So what I need to figure out then is this in order to figure out ACD. Okay? Notice that that x opens up from here. So that kind of helps me start my equation. So I'm going to say half, and those the angles inside of my circle. So I'm going to take those arcs and I'm going to add them. And then that equals 100 degrees. All right, again, I'm going to double both sides. Subtract 120, and I get that angle is 80 degrees. Okay, but what I wanted to figure out was the measure of arc ACD, which is 80 and 60, so 140. Okay, be careful that you don't stop and say that 80 is your answer. Always make sure you go back and check that that was actually the question. All right, so number 4 wants us to figure out angle E, so I'm just going to put an X here. Notice that this angle is outside of my circle. This angle E hits this arc and this arc, so it has 2 intercepted arcs. Very similar to 1, 2, and 3, but instead of adding, since it's outside of my circle, I'm going to subtract. So I'm going to say half of 76 minus 16 is equal to X. Notice that I keep setting up equations. Okay, that means I can put X wherever I want, and I'm always going to be able to solve it. Half of 76 minus 16 is 60. So that means that angle E is 30 degrees. Okay, let's try another one. Let me get rid of this. All right, I want to figure out X and Y. So, notice that X is an arc, We have this arc, we have this arc, and we have this angle that is outside. So again, just like the last one, I'm going to take half, and I always need to take the larger arc first. Okay, I always want to take the larger arc first, otherwise I'm going to subtract and get a negative. So my larger arc is x, it's always the furthest one away, minus 14 equals the angle outside, which is 39. And again, the reason that I'm subtracting is because the angle is outside of my circle. All right, I'm going to double both sides. Gives me 78. Add 14 to both sides. I get 92. Okay, so there's x. Notice I'm not putting a degree with it. X is just a variable. It's representing an angle, though. All right, if I want to figure out y, notice that I already have 14. I already have 115. And I just figured out that this is 92. I'd always go back and label your diagram, which means then y is what's left from 360. So I can take 360 minus 14 minus 115 minus 92, and that will leave me with y. So 360 minus 14 minus 115 minus 92, and I get that y is 139. Alright, so that concludes the front side. That was a lot of just the chord properties, and then angles inside or outside based off of chords. And then this last one is technically a secant. Okay? We have to do this, and then it becomes a secant. Alright, so flip to the back, and now we're going to use the tangent line property. Alright, so there's not many things that we can assume in geometry. We can assume straight lines. We can assume circles are circles and not ovals. When you see line segment AB, because we put a point on the circle, you can assume that that's a point of tangency, which means that if this segment is coming from the center, that means that AQ is perpendicular to AB, which means I have a right triangle, and as soon as we see right triangles, we should be thinking trig or Pythagorean theorem. Okay? If I want to figure out x, which is a side length, I'm going to use I'm going to use Pythagorean theorem. If this radius is 6, then this also has to be 6. If I want to figure out x, I can say my leg squared plus my other leg squared is equal to, make sure you don't take 6 or 4, it's got to be the total distance, which is 10. Okay, so this means that 36 plus x squared equals 100. So x squared equals 64. And x is 8. Now, you can absolutely do that. It didn't take much work. It was pretty easy, especially since the numbers were nice. But you might have also recognized that if this was 6 and this side length was 10, that this was a 3, 4, 5 triangle with a scale factor of 2. Since 3 was doubled to make 6 and 5 was doubled to make 10, then that meant that this one had to be 4 doubled, which is 8. Okay, so again, we should be looking for patterns or shortcuts so that maybe we don't have to do algebra, but it's an option. All right, and the next one, again, we can assume that since there's just one point here, we can assume that this is a point of tangency. So if we connect from W to this point, then we know that these are perpendicular. Okay, so then we have a right triangle where we have a leg of 15. If this right here is a radius of 9, then this also has to be a radius of 9. So we have 15 squared plus 9 squared. And then notice this whole length, we have to use the whole length, not x or 9, is equal to the sum of x plus 9 squared. Okay, in terms of Pythagorean triples, this is none of them, since 3, 4, 5, 3 times 3, and then 4 times 3 is 12, not 15. Okay, so if you think about a 3, 4, 5, if you multiplied it by 3, you'd get your 9, but 3 times 4 is 12, not 15, so that doesn't work. Alright, so I am going to take 15 squared plus 9 squared. I get 306. equals x plus 9 squared. All right, so you have two choices here. You can expand x plus 9, multiply it out, you'll get a quadratic, subtract 306, which is a big number, and then factor. But you can only factor if it ends up being a nice number. Or it's easier just to undo squaring and square root. Okay, so I'm going to leave this as the square root of 306 equals x plus 9, which means x is, I just need to subtract 9. This wouldn't have been factorable, so basically you would have done all that and had to use the quadratic formula, because the square root of 306 is that. Okay, and then I have to subtract 9, so I get that x is about 8.49. All right, so that's two problems with tangent lines. So let's try another one. All right, in this problem, again, I have point R is hitting the circle once, which means I know that this is perpendicular, so a 90-degree angle. All right, notice that I have a side radius of 5 right here, so then that means this also has to be 5. Okay, so if I look at my circle, I can say leg squared plus my other leg squared equals my hypotenuse, which is x plus 5 squared. Okay, 5 squared plus 12 squared is 169, which equals x plus 5 squared. Take the square root, this is 13, which equals x plus 5. Subtract 5, and I get 8. Since the square root of 169 was a nice number, this was a Pythagorean triple, so we didn't really even need to do all this. It would have been nice if we start the problem. Again, look for these patterns. I can see that this is a 5, 12, 13 triangle. Okay, one of my legs is 5, that happens to be my radius. My other leg is 12, which means my hypotenuse must be 13. Well, if I already have 5, then this has to be 8 in order to sum to give me 13. So both of these ways gets the same answer, and this way is a lot less work. Okay, so I mean, I would start looking for patterns. All right, given the diagram to the left, find the length of SR. So if I want to find the length of this, again, start with a formula. The length means that I'm going to be doing arc length, which is circumference. So twinkle, twinkle, little star, circumference equals 2 pi r over theta, times theta over 360. Okay, again, I need two things. I need my radius and I need my angle. Well, I already know my radius, so I just need to figure out my angle. Well, my angle, my theta, I don't know what this arc measure is, but if I figure out what, let's call this y, but if I figure out what that is, it's a central angle, so if that's 30, then my arc measure is 30. Okay, and now this goes back to trig, so I can figure out what that angle is. Okay, and you can use sine, cosine, or tangent from this angle. I'm going to use, doesn't matter, I'm going to use tangent. So I'm going to say the tangent of y is equal to my opposite over my adjacent. Okay, I could also say sine of y equals my opposite over my hypotenuse. Or I could say the cosine of y equals the adjacent over the hypotenuse. So those are the three equations I would use to set up. All of them will give you the same answer. All right, remember that in order to solve this, we have to do the inverse of the ratio. Since I can't take the tangent of y since I don't know what it is, I do the inverse of the other side. So tangent inverse, that's what undoes tangent, of 12 divided by 5. So this tells me that y is about 67.38. Okay, which means if that's 67.38, then this, since it's a central angle, is also 67.38 degrees. Okay, so I can come back to my formula now, and I can say 2 pi times my radius times 67.38 out of 360. Okay, and then put this in your calculator, make sure you're getting the same thing. 2 pi times 5 times 67.38 out of 360. And I get that SR, arc SR, is about 5.88. No measurement, so units. Make sure you're putting units at the end. That way we know that this is a length and not a measure. Okay, and again, I can check to see if that kind of makes sense, because 2 pi r would give me 31.42, which is obviously greater than 5.88, so therefore this actually is a portion of the circumference. All right, two things before you end this video, though. I just need you guys to change two things when you get your homework. In number 1 and number 3, you just need to add two things. In number 1, I want you to find the measure of angle 1 and x, so you're finding two things in that problem. And then in number 3, you're going to find y and x, so both of those things. Okay? Tomorrow we will talk about day 2 of tangent lines, and we'll add a little bit more in terms of properties, or just different ways that you can use the properties. All right, have a good rest of your day, guys.